In previous lectures, we've dealt with some important concepts related to integration. For example, when can a function be integrated and when can it not be? However, the number of functions that we've been able to integrate so far have been very few. So, e to the x, sine x, cosine x, x to the n, and so forth. But we need to be able to find the integrals of many more functions than that because it's important for physics and for mathematics. So in this lecture, we're going to concentrate upon methods, the ways in which we might be able to integrate a given function. Absolutely the best way of doing an integral is to guess the answer. So let's say that we're given some function f of x and we want to integrate this, and that you guess the answer to be capital F of x. How do you know it's right? Well, if you differentiate it with respect to x and you get f of x, then you've got the answer. Let's see how this works out for a number of functions. So let's say that you differentiate this. Then when you differentiate x to the n plus 1, you get n plus 1 x to the power n. The n plus 1 cancels and you get this. If you differentiate sine of x, you get cosine of x. If you differentiate minus cosine of x, then you get sine of x. Well, let's see what happens over here. So let me differentiate minus cosine x plus cos cubed x over 3. And if I differentiate cos x, I get sine x. And if I differentiate cos cubed x, I get 3, which cancelled with this, and I get cos squared x. And then when I differentiate cos of x, I get minus sine x. So then I take sine of x and I get 1 minus cos squared x, and that's, of course, sine cubed x. And that's exactly what's over here. You can easily verify that if you differentiate tan inverse x, you get what's over here. If you differentiate sine inverse, you get this. And of course, this is obvious. That's how you define the exponential. And let's just check this one over here. So let's say that I differentiate x log x minus x. And if I differentiate x log x, I get, when I differentiate x, I get 1, so I get log x. And then when I differentiate log x, I get 1 over x. So the same x is over here and then 1 over x. And then when I differentiate x, I get 1. Now x over x is 1, so it's 1 minus 1, and I get log x. And so I found that the derivative of x log x minus x is log x, and hence calculated this integral. Now obviously you cannot remember everything. Unfortunately, methods have been invented by which we can do certain types of integrals. Let's begin by discussing integration by parts. This is a very common method and a very powerful one which works for some kinds of functions. The idea is very simple. Suppose that I have a product of two functions, f into g, and I take the derivative of f into g. That means I take first the derivative of the first function, keeping the second unchanged, and then take the derivative of the second function, keeping the first unchanged. I could write this in a different notation as well. I could write it as fg prime is f prime g plus fg prime. Both of them are exactly the same, except that in the second, I don't have to say whether I'm differentiating with respect to x or y or t or u or whatever. At the second stage, I'm going to integrate both sides of the equation above. And so I have the integral on the left as the sum of two integrals. So I have the integral of df by dx into g and f into dg by dx. However, this is an integral that I can do. The answer is f of x into g of x. Now I just remind you that if I have the integral of d by dx of any function h of x, well, that's just h of x itself. That was how we had begun in the first lecture on integrals in defining the integral. Now, what that means is that I can simply take one of these integrals to the left side. So, for example, I could have f dg by dx is f into g minus df dx into g, or I could have taken the other integral and written it as follows: df by dx into g, and that's f into g, or f of x into g of x minus dx, and here I would have f into dg by dx. Sometimes this would be more convenient and sometimes this would be more convenient. Now all this will make very little sense unless we work out example after example. Let's keep this formula in front of us and ask how to do this integral, x into the exponential of x. Here I can very easily write this as d by dx of e to the x. And so then I have something that's exactly of the form above, provided I have f of x is x and g of x is e to the x. So the right-hand side of the integral, so the thing that we're trying to find out, is f into g, which is x e to the x, and then I have to subtract from this df by dx into g. But df by dx, if we look over here, f of x is x, that's 1. So I have only g left, and that's e to the x. But the integral of e to the x is e to the x itself. And so we have x e to the x minus e to the x. And if you like, you can just simplify this slightly, and that's the answer. So we found that the integral of x e to the x is equal to this. And you can check that this is right. Simply differentiate this over here, and you should get x e to the x. Actually, that's quite obvious from here. Now let's take a slightly different function. Here, instead of x, I have x squared. Again, I'm going to write e to the x as d by dx of e to the x. And so the integral of x squared e to the x will be f into g, but now I'm taking this over here to be f, so that's x squared e to the x, and then I have to subtract from this the derivative of f, so that's 2x, and then have g I'm taking to be e to the x, of course, and so this is x squared e to the x minus 2 times the integral that we had calculated in example 1. And the answer then is x squared, and you remember that this, you can see from the above that this is x e to the x minus e to the x. And so this is x squared minus 2x plus 2 e to the x. Let's now think of something even more complicated and go on to any power of x. So x to the power n is integer, times e to the x. Again, I'm going to take this e to the x as being d by dx of e to the x. So in other words, I'm going to again take g to be e to the x. And so this is f is x to the n, times e to the x, minus, and now I need to differentiate this first function. So this is my f over here. When I differentiate f, as I must according to this formula here, up above, here, then I get n x to the n minus 1, and then I write g, of course, as e to the x. This is x to the n e to the x minus n times x to the n minus 1 e to the x. Here is something that's quite interesting. Let me call this thing as in. Well, that says give me an integer n, and the meaning of that is the integral of x to the n e to the x. Then if I've defined in that way, then obviously this is in minus 1. And so what we've discovered is that in is x to the n e to the x minus n times in minus 1. Now this is saying that given I1, I can compute I2. Give me I2, I can compute I3. Give me I3, I can compute I4, etc. And this is what is called a recursion relation. Now take this integral. Here, obviously, I can write cosine of x as the derivative of sine x. And so using the formula above, I can write x cosine x first as the product of the two functions x into sine x, and then I need to subtract away from this the integral, the derivative of f, which is 1, and then I write the second function as it is, sine x, but the integral of sine x will be minus cosine x. So I get x sine x plus cosine x. And now you can easily check that if I take the derivative of x sine x plus cosine x and do the differentiations, then I will get x cosine x. So this answer is indeed correct. Well, let's go on to a slightly more complicated example, and this is x squared sine x. And of course, I want to write this as d by dx of cosine of x, well, with a minus sign. And so I will write this as follows. I'll write this as minus x squared cosine of x minus, and now I need to differentiate the first function, which is 2x, write the second function as it is, which is minus cosine x, and so this gives me minus x squared cos x plus 2 times the integral of x cosine x. But then I have already computed this above and found this to be x sine x plus cosine of x. And so if I now simply take this common 2 minus x squared and multiply it by cosine x, and I have here 2x sine x. So that's the answer. And again, you should check to see that if I differentiate this, I get x squared sine x. We've now applied this integration by parts formula a few times now. But look, there are two functions here, f and g, and there's a relation between this integral to the left and this integral to the right. But how do we use this formula to calculate this integral here? Because now there seems to be only one function, log of x. But actually we can fix this quite easily, because if we write log of x times 1 in this form, so let me write d by dx of x, that's 1. Then I have exactly the kind of thing up above over here, and so this is x log x minus the integral. So now I have to differentiate log of x with respect to x, that's 1 over x, and then write this function g of x, but g of x is what we're taking over here. And so that's x, and now that's just the integral of 1, and so we get x log x minus x. And you can easily check by differentiating that this is the right answer. Now, let's do something a little more complicated. Log of x squared. Again, we shall use exactly the same trick. Dx, and then log of x squared, d by dx of x. And so this is obviously x log of x squared. And then we subtract from this. Now we have to differentiate log of x squared, and now that's 2 log of x. And then we have to differentiate log of x, so that's 1 over x, and then write g, that is to say x. And so this is x log of x squared. But this function, 2 dx log of x integrated, we've calculated above, and so we can write the answer as x log x squared minus 2 times what's above, and so that's 2x into log of x minus 1. This gives us the idea that maybe we can do a more general calculation. And so let's look at this integral here, log of x to the power n. And we shall, of course, use our trick now to write this as x log of x to the power n, and subtract, of course, this. Now when we differentiate log of x to the n, we get n log of x to the power n minus 1, and then we differentiate log of x, we get 1 over x. We put the x as before, and so that's 1 over there. Again, we have a recursion relation. So let's define in to be the integral of log of x to the power n. And so what we've discovered is in is n log of x to the power n minus n times n minus 1. And so that's something that's quite interesting we've discovered, that there's a recursion relation for this integral as well. Integration by parts sometimes puts us into new situations where one has to think where to go next. Let's take this integral, for example. So here I have e to the x cosine of x. I'm going to write cosine of x as d by dx of sine x. And so I'm going to have then, using the formula up above, that this is e to the x sine x, and then I have to subtract out this thing, dx. Now when I differentiate e to the x, I get e to the x again. And now I have sine x. Okay, so I'm not in a very much better situation than before, because earlier on it was e to the x cosine x, and now I have to deal with this integral, e to the x sine x. So how do I deal with this? Well, let me write this as d by dx of minus cosine x. And so here is a situation then where I can use another integration by parts. So let's do that for the second one. And here I have e to the x and minus cosine x, and there's a minus outside, so that's a plus. So that gives me plus e to the x cosine x. And then I have to subtract out. So I'm doing integration by parts on this integral over here. I have e to the x and cosine x. So here's a nice situation. I have e to the x cosine x over here, the same thing over here, fortunately with a minus sign. And so I have, taking it to the left side, 2 dx e to the x cosine x, and this is e to the x into sine x plus cosine x. And so I have now solved the problem. What we've discovered is that this integral is just half of e to the x sine of x plus cosine x. Now, of course, one can check this, just differentiate this, and you will get that. Let's now come to a second way of doing integrals. It's called integration by substitution. So here is the integral that we really want to solve, find the value of, but maybe it's not possible to do it in the way that it's written. Therefore, it is sometimes useful to write x as a function of a new variable. You could call it t or u or y or whatever. We'll call it y. In which case you could write dx as dx by dy into dy, put it in up above over here, and so you get dx f of x now as the integral of dy dx by dy, and now the function f depends upon x, but x depends upon y, so you could say it depends upon y. Now maybe this second integral, or rather the form in which this first integral has been put into, is easier to solve. There's no guarantee, but maybe this one over here could be used and could be solved more easily. Now what I've outlined over here is a way of remembering things. That's why I called it a sloppy proof. It's not even a proof, it's just a way of remembering things. But now, before we use this integration by substitution trick, let me give you a proper proof. So, suppose that we call the integral of f of x as capital F of y. Now, of course, you remember what this means is that the derivative of capital F has to be f of y. Now, it doesn't matter that here there is y or x or t or u. Remember that these relations hold for whichever symbol is used. Now, the next step is to write this as df of y by dy. However, now I can use the chain rule. So I use the chain rule at this point and write df by dy as df by dx into dx by dy. And so, writing f of y, and you see y depends upon x, and so this over here is also equivalently f of y of x. So this depends upon x. Therefore, what we've discovered is that the integral that we are looking for can be written as this. And so here is the proper proof. But this is, as I said, the easier way to remember integration by substitution. Now let's use the substitution method that we've just discussed, beginning with this first example. Let me make the substitution y is equal to cosine of x. I could have written this as x is cosine inverse y, but both of them, of course, are equivalent. Let me then write dy as the derivative of cosine of x, which is minus sine x into dx, and put this sine of x dx up over here. So I get dx sine x cosine of x to the power 6 as being minus, and now I have dy, and cosine of x is of course y, so I get y to the 6th. And now anyone can do this integral. This is minus y to the 7 over 7. However, I must put back over here y equal to cosine of x, and so this is minus 1 over 7 cosine of x to the power 7. You notice that if I differentiate cosine of x to the 7 over 7, I get exactly what's in the integrand over here. So the method of substitution has worked very well. Why did I choose y equal to cosine of x and why not y equals sine of x? That, if I had chosen y equal to sine x, things would have just become more complicated and nothing would have worked. So you have to make the right choice of substitution. Now move on to the second example. Here I have x squared plus 4 to the power 4 and dx into x. Now, of course, I could open out x squared plus 4 to the power 4 and I'd get a polynomial in x, but that would be a very ugly way of doing this. Instead, let me write y equals x squared plus 4. Immediately I see that dy is equal to 2x dx, and so this x dx factor is already over here, and therefore my integral, which is this x squared plus 4 to the 4, becomes half integral dy. So x dx is half dy, and here I have y to the power 4. And this we can integrate very easily. It's half y to the power 5 over 5. And so that's y to the 5 over 10. On the other hand, y is x squared plus 4. So this is x squared plus 4 to the power 5 divided by 10. And that, of course, is an answer that you can easily check to be correct by differentiating this side. I think you would have got the idea by now. Here, let's put y equal to x to the power 4 plus half x squared. And you see that this choice makes things very simple because I have dy equals now 4x cubed plus x dx. And this is exactly what we have over here. Therefore, we have dy, and x to the 4 plus half x squared is already y, so this is y to the 6th, and that's y to the 7th over 7. Let's substitute y as x to the 4 plus half x squared, and this gives us 1/7 of x to the 4 plus half x squared to the power 7. Next, it's going to be very similar. We'll put y equal to x squared over here. And so dy is 2x dx. Again, you see that x dx occurs over here. And so we have dx, x sine of x squared as dy. And there's a half. And the only thing here is then sine of y. Integral of sine of y is minus cosine of y. So I have minus half cosine of y. And the next thing that we need to do is just substitute x squared. So this is minus half cosine of x squared. How would you do an integral like this, where you have the inverse of sine? Of course, the inverse is also called the arc sine, but that's just another name. Instead of writing y equal to something, I'm going to write x as sine of y. Of course, I could have written y equals sine inverse of x. You can go from x to y or y to x. Now I can write dx as cosine of y dy, in which case the integral that I'm looking for, which is sine inverse of x, let me put in dx, that's dy cosine of y, and now sine inverse of x is y itself. Now this is an integral, y into cosine of y, which we've learned how to do. You can immediately write down the answer. It's y sine y plus cosine of y. You can check by just differentiating this answer over here, and you will get y cosine y. Now, the only thing that remains is to substitute in y. Y is sine inverse of x, and sine of y is, of course, x itself. So I have x sine inverse of x. And now cosine of y is the square root of 1 minus sine squared of y. But sine of y is x, so this is 1 minus x squared under root. And that is the value of this integral of sine inverse of x. Let's make a similar substitution in this next one here. What if I take x to be tan of y? In that case, y is tan inverse of x. And now I have to remember that when I differentiate tan of y, I get 1 over cosine squared y or sec squared y. So I have dx is 1 over cos squared y dy. Let me put this into this integral here. So I have integral dx tan inverse of x over 1 plus x squared. Now, when I substitute dx, I'm going to get dy 1 over cos squared y. Tan inverse of x is y itself, so that's y on top. And then I must put 1 plus x squared, which is 1 plus tan of y squared. But tan of y is sine of y squared over cos squared y. And all this is together. Now I take cosine squared y inside. So this will become cosine squared here. And that cosine squared will cancel out what's over here. So this is integral dy y. And at the bottom, I have just cos squared y plus sine squared y. But cos squared y plus sine squared y is 1. And so I get the integral of y, which is half y squared. But we've already seen that y is tan inverse of x, and so this is half tan inverse of x squared. And that is the value of this integral here. Now, in both of the integrals above, I had chosen x as something defined in terms of y. But of course, as I said earlier, you can go from here to here and here to here back, or from here to here. Now here's an integral that looks apparently very complicated. There is an exponential of sine of x. Fortunately, we recognize that dx cosine x will be just d of sine x. That's really crying out for the following substitution. Let's write y equal to sine x, and in that case dy will be cosine of x dx. So cosine of x dx can be simply written as dy, and hence we can easily spot the value of this integral. It's now almost done. Cosine of x dx is dy, and e to the sine x is e to the y, and so this is just e to the y, and y is sine x. Of course, you could have simply guessed this answer, e to the sine x, differentiated it, and you would have got this integrand up above over here. So that was easy. What about here? Now, again, we shall do the obvious substitution. Let's put y equal to e to the x, and then dy will be e to the x dx, which is the same as y dx. And this integral up above is therefore dy 1 over square root of 1 minus e to the 2x, and that's y squared. But you recognize this is just sine inverse of y. That's because if you differentiate sine inverse of y, you get 1 over square root of 1 minus y squared. And so the only thing that remains is to write down the final answer, sine inverse of e to the power x. The crucial thing is to remember the derivative of sine inverse as being this. So let me just repeat that. This is something that you should remember, that the inverse function, the arc sine of y, the derivative of that is this. We've had so much practice now that this integral is going to be really easy. Let's put y equal to log of x. And of course, we could write it the other way as x equals e to the power y. Then dy will be 1 over x into dx. So it's dx over x. In which case, the integral that we want, which is dx over x into 1 over log of x to the n, this is then just dy into 1 over y to the power n, or y to the power minus n. And we know how to do that very easily. That's y to the minus n plus 1 over minus n plus 1. And so just put in y equals log x. So we get log of x to the 1 minus n divided by 1 minus n. That was easy. Here's another easy example, and the last one that we look at. Again, the substitution is obvious. Y should be taken as tan x. If you took it as something else, it wouldn't work. or it would make the problem harder. What we want to do is to make the problem easier. We've seen earlier that when we differentiate tan x, we get sec squared x. And now you see sec squared x over here is exactly what we have over here. And so we have dx sec squared x tan to the 7x is simply dy, and tan x is y, so that's y to the power 7, and this gives us 1/8 of y to the power 8, which is tan x to the power 8 divided by 8. And so we've been able to solve a lot of problems using the method of substitution. Of course, you have to think of what is the correct substitution to make. If you choose the right one, your task will become easier, and if you choose the wrong one, then you will get nowhere. As you saw in this lecture, integration is a bit of an art. It's not like differentiation. Differentiation is very automatic. But here, what sort of substitutions should you make? How should you integrate by parts and all that? It's a bit tricky. And in fact, you don't even know if the function that you're trying to integrate has a simple answer. So for example, integral of e to the minus x squared looks simple, but in fact, that integral cannot be done in terms of simple functions like exponentials or sine or cosine and so forth. Therefore, we shall have to continue our pursuit of more methods, and that's what we'll do in the next lecture.